We have covered some of the fundamental problems with the atom and looked at how the structured atom model solves many of these issues. We have also wondered what exactly a charged particle, either a proton or an electron, actually is. The electron has some very strange properties that define many aspects of accepted science. While researching, I came across this paper by Michael Singer, who has put together a very comprehensive piece outlining some of the issues regarding electrons, acceleration, and the production of electromagnetic radiation. Let's run through his paper and get a better understanding of what these issues are. We know that charged particles emit electromagnetic radiation as a function of their acceleration. There are, however, some rather glaring exceptions to this. Some believe that classical electromagnetism cannot be used to describe atomic behavior because it requires that an electron radiates energy under acceleration, and this would mean that the electron would eventually fall into the nucleus. But why would a charged particle radiate under one condition but not the other? Any complete model of the universe must be able to predict precisely which behaviors occur or accept that that model of the universe cannot be complete. The original concept that particles radiate electromagnetic energy seems to have arisen in an attempt to describe how X-rays occurred back in 1895. At the time, the Thomson-Plum model was used, and it was believed that the electrons smashed into the plum pudding and came to a dead stop. Using this model, the only possible explanation for the X-ray was that the extreme deceleration during the impact had generated the radiation. This idea has become so embedded in the scientific consciousness that little critical analysis has ever been carried out to determine if this does in fact occur in this way. The first real challenge to this concept came with the theory of relativity, and then later on by Rutherford when he proposed a different model for the atom with a positive central charge orbited by negatively charged electrons. Applying relativity to linear accelerative radiation. If we consider the simple scenario where an electron is accelerated from the observer's rest frame up to a velocity v and then decelerated back to zero in the observer's rest frame, let's also assume that this acceleration produces radiation. There is a certain amount of energy required to accelerate the electron to the velocity v, and let's call this Ek. There will also be a certain amount of energy that is radiated by the particle, and let's call this Er. This means that the amount of energy required to get the electron up to the velocity v is Ek plus Er, if the principles of the conservation of energy is applied. This radiation will escape the system, so we have supplied Ek plus Er and are left with only Ek after Er escapes. Next, we will decelerate the electron. According to relativity from the electron's frame of reference, it is simply undergoing more acceleration, just in a different direction. So again, we must supply an amount of energy to slow the electron down, and in this case it's once again Ek. And once more the electron will radiate a fixed amount of energy, which we will call Er. The radiation escapes, leaving the electron at rest in the observer's rest frame. So the total amount of work done in the observer's rest frame is the first step, Ek plus Er, and the same amount of work is returned to the frame in the second step. So overall there is no net work done in that frame. But two ERs escape the system. This process either violates the principle of conservation of energy, and an accelerating charged particle is a source of free energy, or Er must be zero. In other words, there is no accelerative radiation. If accelerative radiation did exist, we will be able to create a source of infinite energy by simply having a charged particle bounce back and forth between charged end plates, radiating energy as it does so. For accelerative radiation, when the particle is being accelerated by an outside force, momentum considerations will require it to radiate more or less in the direction of acceleration. By contrast, a particle slowing down by itself, due to the radiative losses, would radiate energy in the opposite direction to the acceleration, in order to conserve momentum. Relativity does not allow us to pick and choose like this. Applying relativity to the circular accelerative radiation. Let's now consider an electron orbiting around a positively charged central point. The question now becomes, does classical electromagnetism demand that the electron radiates and thereby loses kinetic energy spiraling into the central charge? The electron is orbiting because the force it experiences towards the central charge causes its path to be constantly changed, creating a circular path. Its velocity is constant, but its displacement is not, and therefore it is accelerating. If it were to slow down and spiral into the central charge, it would have to radiate along the direction of its velocity so that it would carry momentum away from the electron. Let's consider this from the electron's frame of reference. It feels a force towards the positive charge. For the electron to decelerate, it must emit radiation in the forward orbital direction. This is not only at right angles to the acceleration, but in one specific direction out of 360 degrees of possible directions that are at right angles to the acceleration. Now consider an electron that was not orbiting, but simply accelerating towards the positive charge. Now the electron would radiate energy at right angles in one specific angle, and this would cause the electron to start orbiting. If we now apply the same rules from the previous section on linear acceleration, but assume radiation occurs, then the work done in radiating the energy must be provided by an increased centrifugal force. So the electron would orbit at a lower speed for any specific distance from the central charge. It would not fall into the central charge, but emit radiation continuously towards it. Hence, in this model, we would see continuous radiation coming from atomic structures and a consequential violation of the principle of conservation of energy. These issues imply that there might be a fundamental flaw in this concept. Accelerative radiation is assumed to be a lossy mechanism that takes energy from the accelerating charge. If we consider a simple spring system with a mass on one end, when the system oscillates, the spring provides a force which changes depending on the position of the end in relation to the attach point. The mass provides a force that is a function of its acceleration or deceleration. Together these would allow the spring to oscillate forever in a perfect system where there is no loss associated with any part of the system. If we introduce a damper, then we can remove energy from the system over time, but the amount the damper can extract is directly related to its velocity. If we therefore consider this with respect to the electron, then there must be some sensitivity to velocity. The problem is that any accelerative radiation is a function of the electron's acceleration in its own reference frame. But it is always travelling at a zero velocity in its own reference frame, so such radiation cannot be lossy. Consequently, any radiation emitted cannot act to remove energy from the system. In part 2, we will examine some known examples that are thought to radiate energy through acceleration and see how this may not actually be the case. As always, be brave, be curious, the truth is waiting for us. Until next time.